You know, people are like getting pictures of different people and trying to put them into like things that people might not like. My schedule this semester. You guys need to take first. Well, I did it first. I'll just do switch up. I should do this.
I know. I know how long it's
I want to only have one. Yeah, no, I just need to really it's 7 bucks.
I'm not gonna work small. Medium or larger cows.
So we're gonna get a class and we're gonna do a half, like a public half circle. So we have to do that. Wednesday we have
Well, it's like hard.
And as soon as I think this one person that is okay, I'll move to the next section and there's just I got it. It's the entire time. It's just charge up the prices. What upsets me is that why is it that's the seriously. It's not.
Okay, I hope you had a good fall break. We now will push our way through till Thanksgiving break. And Thanksgiving break basically will fall at about a time where we are finishing up most of the material for the semester. So we've got a lot to cover in a very short period of time. That being said, you have to be on top of your game. So what do we have to cover before spring? I mean, spring break. Before Thanksgiving break. We will finish up with our discussion of weak acids and weak bases, which really is not finishing up the discussion. It is finishing up the discussion on the pH of a weak acid. If I were just to add it to water, what is it? We have to discuss Lewis acids and bases. We have to discuss whether a ionic salt is an acid, a base, or neutral. We have to discuss buffers and titrations. We have a discussion on the energy associated with the reaction. So Gibbs free energy, delta H, delta S, and so many more things. And then we also have electrochemistry. So there's a lot of information that we'll discuss. One of the things I wanted to let you know is that you will not have to do the pre-lab for this week's lab. And the reason you don't have to do the pre-lab is because we haven't gotten to the sectional buffers. So I'm going to actually spend about an hour of our lab tomorrow discussing buffers. And it is going to be through some of these labs where we start to cover some information that will not be covered, and then I won't cover that information in class. So that is one thing you need to be aware of. Another thing that you need to be aware of, and I believe I put it as Wednesday. Wednesday, your first draft of everything is due. So your first draft of the ACS document, the first draft of the grant worksheet, and the first draft of my document for your service learning project is due. It was announced last week. It's been on the calendar since the beginning of the semester. Now, I've had questions about my document, what that is. I did not have a template like the ACS had, so I gave you an exact example of what I'm looking for. And basically, you're going to replace my information with your information on that document. So again, that is due on Wednesday at 11:59 p.m. I actually extended it because it was originally due before that. So, but because fall break was happening, I went ahead and extended it. So there is a lot we need to cover over the next few weeks. And so I am going to get started in today's information as soon as I pass around the sign, because I forgot to pass around last Wednesday. Okay, so on Wednesday of last week, we talked about strong acids and strong bases. We talked about their dissociation. If you have a strong acid or a strong base, they're going to dissociate entirely in water, meaning the concentration of the acid is going to be equivalent to the concentration of the hydronium ion. Or if you have a base, the concentration of the base is going to be equivalent to the concentration of the hydroxide ion. From knowing the hydronium ion concentration or the hydroxide ion concentration, you can determine the opposite ion concentration using Kw is equal to the hydronium times the hydroxide. You can calculate the pH of the solution. pH is equal to the negative log of the hydronium. And you can calculate the pOH using a variety of methods. And so we did that on Wednesday prior to fall break. Today, what we're going to do is we're going to be looking at weak acids and weak bases. Weak acids only partially dissociate in water to form hydronium. Weak acids set up an equilibrium. So the information that we were discussing about equilibrium or solutions of equilibrium is going to come into play when we're talking about weak acids. One thing you need to be prepared to do is you need to be prepared to predict or develop the products of a weak acid dissociation in water and a weak base dissociation in water, or as when we get to titration, how an acid base interact. So with the weak acid is going to donate its proton to form hydronium ion, and the conjugate base, which will be the negative ion of the acid. Now, if I say that you have 0.05 molar benzoic acid, which is what this acid is, I want you to be able to determine the pH, pOH, hydronium concentration, and hydroxide concentration, just like I do with a strong acid and base. Now, to be able to do so, we're going to have to understand equilibrium. And we're going to have to develop a Rice table. So if we initially have 0.05 molar benzoic acid, we have none of our hydronium and none of our none of our benzoate. And as far as water is concerned, because it is a liquid, it does not have any impact in the equation.
Now, when benzoic acid dissociates, it's going to lose 1x. The fact that it loses 1x is directly associated with its coefficients of the balanced chemical equation. Again, there's not going to be any impact due to the water. We are going to gain 1x of the hydronium, and we are going to gain 1x of the benzoate. So that at equilibrium, we have 0.05 minus x of the benzoic acid. Water, again, has no impact. We have x of the hydronium, and we have x of the benzoate. We can develop a Ka expression because this reaction is an acid at equilibrium. The Ka expression would be that it would be the hydronium concentration times the benzoate concentration divided by the benzoic acid concentration at equilibrium. Your Kas can be found in the appendix in a textbook. In this textbook, it's Appendix 2. And it is table C1. Now, if you don't have the textbook, because I don't actually require the purchase of the textbook, you can go online and look up acid dissociation constants. Now, when I look up the acid dissociation constant for benzoic acid, it has a value of 6.5 times 10 to the minus 5. That's going to be equal to x for our hydronium times x for our benzoate, and divided by 0.05 minus x for our benzoic acid. We then multiply through by the denominator. When you multiply 6.5 times 10 to the negative 5 by 0.05, that is 3.25 times 10 to the minus 6 minus 6.5 times 10 to the minus 5 times x is equal to x squared. We rearrange to set the equation equal to 0. And I do so that the x squared value is a positive value. So in that particular case, 0 is equal to x squared plus 6.5 times 10 to the minus 5x minus 3.25 times 10 to the minus 6. We then use the quadratic equation to solve for x. Our a value is associated with x squared, so that is a 1. The b value is associated with the x, so that is a positive 6.5 times 10 to the negative 5. And our c value is the constant value, so it's a negative 3.25 times 10 to the negative 6. When you key this in, only one of the values is going to be valid, and it's going to be the value that allows x to be number one, that is going to make sure that X is a non-negative digit is the key. You can't have a negative concentration. So in this case, the only acceptable X value is 0.00177. That, folks, is equal to your hydronium concentration according to your ICE table. Now we can figure out our hydroxide concentration because Kw is equal to the hydronium concentration times the hydroxide concentration. Unless I tell you otherwise, you're going to use the Kw of 1 times 10 to the minus 14. Basically, we're going to assume our equilibrium constant is at, our reaction is occurring at 25 degrees Celsius. So that is going to be equal to 0.00177 times the hydroxide concentration. So our hydroxide concentration is equal to 1 times 10 to the minus 14 divided by 0.00177, or in other words, it is 5.65 times 10 to the minus 12. Yes.
Will we be given 6.5 times 10 to the negative 6 on the test?
You will be given the equilibrium constant on the test, yes. Now, to get the pH of this solution, pH is equal to the negative log of the hydronium concentration. So it's equal to the negative log of 0.00177. So our pH comes out to be equal to 2.75. Finally, the POH, we can get that using 14 is equal to the pH plus the POH. So 14 is equal to 2.75 plus the POH. So our POH comes out to be equal to 11.25. Now, you should always look and see if the information you are obtaining makes any sense. We have a weak acid in the form of benzoic acid. It had an equilibrium constant of 6.5 times 10 to the minus 5. That means that it is weak, but it's not that weak if you think about the options available to us, which is, I mean, we can go down to 10 to the minus 36. So if you think about it from that perspective, it's weak, but it's not that weak. So the fact that our hydronium concentration comes out to be 0.00177 is not out of the realm of possibilities, because we're thinking, well, if it's not that weak, it's going to dissociate a reasonable amount. So we're going to have a reasonable amount of hydronium. What is reasonable? It depends on the Ka. But again, if you're talking about a 0.00 something concentration, that's again a relatively decent sized concentration. the fact that we're looking at something above 0.001, if it was just 0.001, it would have a pH of 3. But because you're looking at 3/4 greater, that's why it is 3/4 greater. So 2.75 does make sense. And then if you've got a decent pH, then you would expect a very small POH. So you should always kind of look through and say, does the numbers make sense? Questions? Okay. Now, before I move into the next piece, there is one other equation that you need to be familiar with, and I derived it. But I'll derive it here too. So if we let's take something as simple as acetic acid. When acetic acid is added to water, it dissociates to form acetate ion plus hydronium. We can write an equilibrium constant for this, that the Ka is equal to the acetate concentration times the hydronium concentration divided by the acetic acid concentration. We know in this particular case that this is an acid, so this would be the conjugate base. If I put that conjugate base in water, it's going to act as a base, and therefore the water is going to be acting as an acid, donating its proton to the acetate to set up an equilibrium of that forms HC2H3O2 as the conjugate acid, and hydroxide as the conjugate base. We can write an equilibrium expression, and because we are starting with the base, we would write a Kb expression. The Kb would be equal to the acetic acid concentration times the hydroxide concentration divided by the acetate concentration. Now, if we multiply Ka times Kb, that would be equal to the acetic acid concentration times the hydronium concentration, the acetate concentration times the hydronium concentration divided by the acetic acid concentration times the acetic acid concentration times hydroxide concentration all over the acetate concentration. Now, looking at this, the acetate concentration cancels out. The acetic acid concentration cancels out. So Ka times Kb is equal to the hydronium concentration times the hydroxide concentration, or in other words, it's equal to Kw. So more frequently, it's written as Kw is equal to Ka times Kb. This is the proof to the equation that we actually are going to use. Now, why do we need KW is equal to KA times KB? The reason you need KW is equal to KA times KB is because you may or may not have a KB table. So you need to be prepared to use the KA table. And then use this equation to convert between KA and KB if you're dealing with a conjugate base. So let's look at an example. A 0.65 molar solution of lactate, sodium lactate, is added to water. What is the hydronium concentration, hydroxide concentration, pH, and pOH of this solution? By the way, folks, be prepared to know that if I say or write the word hydronium, that hydronium is H3O+. If I say or write the word hydroxide, hydroxide is OH-. Because I may write the formula for hydronium, or I may just say the word hydronium and expect you to solve accordingly. You need to know who's who. And the only reason I'm saying that is because I've seen many a time where students confuse who is hydronium and who is hydroxide. Okay, so the fact is sodium lactate, being a sodium salt, dissociates entirely into sodium ion and lactate ion. When we are throwing sodium lactate in solution, it is the lactate that is going to be setting up an equilibrium. So the lactate is being added to water to form lactic acid, and hydroxide. You're not going to find the you're not going to find the KB for lactate. But we will find that the Ka for lactic acid is 1.4 times 10 to the minus 4. Now, when we deal with our rice table, we started out with 0.065 molar of our lactate. The water doesn't matter. None of our lactic acid and none of our hydroxide. The change is we lose one lactate to form one lactic acid and one hydroxide. So at equilibrium, we have 0.065 minus X of the lactate. We have X of the lactic acid, and we have X of the hydroxide. We can write an equilibrium expression, but it's equal to the Kb because that is the reactant. And that is going to equal the lactic acid concentration times the hydroxide concentration all over the lactate concentration. Again, you're not going to find Kb, so you're going to have to use the fact that Kw is equal to Ka times Kb in order to be able to determine what Kb is. Kw is 1 times 10 to the minus 14. That is equal to 1.4 times 10 to the minus 4 times Kb. So Kb is equal to 7.14 times 10 to the minus 11. So going back to our Kb expression, 7.14 times 10 to the minus 11 is going to equal X for the lactic acid times X for the hydroxide all over 0.065 minus X for our lactate. We're following the same steps we followed earlier, so we're multiplying through by the denominator. And you get 4.64 times 10 to the minus 12 minus 7.14 times 10 to the minus 11 times X is equal to X squared. We're rearranging the equation so that 0 is equal to X squared plus 7.14 times 10 to the minus 11 times X minus 4.64 times 10 to the minus 12. Using our quadratic equation, A is 1, B is 7.14 times 10 to the minus 11, and C is a negative 4.64 times 10 to the minus 12. Keying that in, you get an X value of 2.15 times 10 to the minus 6. And folks, that is equal to your hydroxide concentration according to your rice table. Does that number make sense for hydroxide? When you think about the fact that we are talking about a Kb that is so small, you would expect a fairly small concentration of products. Now we're going to use Kw is equal to the hydronium times the hydroxide. So 1 times 10 to the minus 14 is equal to the hydronium concentration times 2.15 times 10 to the minus 6. Or in other words, the hydronium concentration is 4.65 times 10 to the minus 9. Your pH is equal to the negative log of the hydronium. So it's equal to a negative log of 4.65 times 10 to the minus 9. So that is equal to 8.33. Lastly, your pOH, 14 is equal to the pH plus the pOH. So 14 is equal to 8.33 plus the pOH. So your pOH comes out to be equal to, I don't know what. 5.67. Again, does this information make sense? A pH, according to the pH scale that we had designed or had looked at, 7 is neutral. And that correlates to 1 times 10 to the minus 7 for our hydronium concentration. Anything larger than 7 is equal to, is basic. And it is equal to hydronium concentrations smaller than 1 times 10 to the minus 7. And anything less than 7 is acidic. And it correlates to hydronium concentrations greater than 1 times 10 to the minus 7. So thinking about our pH scale, first of all, what type of material did I start with? Well, I started with the sodium lactate. The sodium lactate dissociated entirely into what? Lactate, which is a base. So I need everything to wind up, this information to wind up here for our hydronium. So our pH got to be greater than 7. And it was. Our hydronium concentration better be less than 1 times 10 to the minus 7. And if you look at that hydronium concentration, it is. So at least from a numerical standpoint, it makes sense because again, you started with a base. Questions? Yes.
Where does the sodium come in? Not associated with.
It's still in solution. But sodium, lithium, potassium, rubidium, they don't play a role in what is really going on in solution because they're all soluble salts. They're soluble all of the time. There's really no exceptions to that rule. Questions? So, one of the key things that you got to know is, are you dealing with an acid or are you dealing with a base? Do you need the Ka or do you need the Kb? So if I say, if I give you a 0, what are you doing to me? 0.05 molar HBRO. And I say the Ka, when I give you the Ka, I will say the Ka for HBRO is equal to 2.8 times 10 to the minus 9. I'm essentially telling you, hey, this is an acid. But if I were to give you 0.0769 molar C6H5O minus with a Ka of HC6H5O being 1.3 times 10 to the minus 10. I've given you the acidic form, and I gave you the basic form. I'm telling you, you're working with a base. In other words, I'm going to have to tell you what I'm working with. Is it the Ka and what for on a test? Now in class, you can look it up. For homework, you can look it up. But for a test, you will be given Ka information to work with. You just need to be able to compare basically formulas to know what you're working with. Questions? Folks, what we did today is very similar to what we did about, I don't know, 3 or 4 lectures ago, where we were looking at the concentration of something at equilibrium. It's just when we're dealing with acid-base chemistry, when we're just dealing with the weak acid only, that's something at equilibrium is hydronium. When we're dealing with a weak base only, that's something at equilibrium is hydroxide. Any questions for me? If not, then that's all I have for today.
Over that.